Hello everyone. Welcome back to the session on your process synchronization. We are unit 4 part 1. So I think you people have now a clear idea with respect to your process synchronization. What do you mean by synchronization exactly here? So in the previous section we discussed about something, the basic introduction part, the introduction part of your process synchronization, where we have actually represented that what even the synchronization is nothing but when multiple processes will we have a concept something called as critical section, right? And the multiple processes will be trying to access that particular critical section. And our task is to make sure that whenever one of the process enters in the critical section, no other process should be allowed to enter in the critical section. So basically, you might have got awareness related to your critical section. What do you mean by critical section here is, your critical section is nothing but it is actually a small execution part, or you can say it is an execution code, small block, okay, where the process will be doing the task for which that particular process is actually created. So that is what we call it as critical section. And we also said that whenever process enters into the critical section, no other process should be allowed to enter into a critical section. They have to wait until that particular process is releasing it. Because if some other process is allowed to enter into the critical section, then definitely there might be some problems with respect to the synchronization. That is, whatever the update that process P1 might be doing, at that time we give that region to process P2, then there is a possibility that there might be infringements when we are executing that particular code. So in order to make sure that particular thing doesn't happen, we need to synchronize all the processes. Indirectly, what it means to say is we have to overcome the race condition of these processes. We have to overcome this particular race condition of processes for entering into critical section. That is what basically we are going to do in this particular scenario, right? So in the previous section, we discussed about something related to your critical section problem. I think you people know what is the problem here is. We need to design a solution. We need to design a solution or a protocol which should be used by all the processes. Yeah. In single terminology, if you ask me to say, I can say that to avoid race condition. To avoid race condition from entering into critical section. Okay, so that is the main design. Okay, what is the problem here is that making sure that not all the processes simultaneously try to enter into the critical section. That is the problem here. So for that we need to design a solution, or we can say that basically we need to design a protocol, and based upon that protocol, and this protocol should be used by each and every process which is getting created in that particular system. They have to follow this particular protocol. I think you basically know what I mean by protocol is nothing but set of rules. So they have to follow these rules in order to get that particular process get executed. So for that purpose, we need to design a protocol, and that's for the problem. And for that, we have already seen one protocol. Means what is the solution? We have seen a software solution, right? We have seen a software solution which is famously called as Peterson's solution. Peterson solution in the previous video. Now in this particular Peterson solution, anyhow it has a limitation related to with respect to for its execution, but still we saw how it exactly works. Okay, we know that it is restricted only to two processes. In between two processes only we can apply this particular Peterson solution for your critical section problem. But the way it actually elaborates or way it exactly explains the concept, it becomes provides wider area. It provides a wider area to determine or to create the different solutions for your critical section problem. So basically remember that it is a software solution. And anyhow, we cannot apply this particular Peterson solution to your modern computer systems because of its architecture. Because of its architecture, since there are only two processes, whenever we have only two processes executing, we can apply this particular solution. So we can't, because today's generation, the systems actually support multiple architectures, right? Multiple architecture, I mean multiple processes are actually getting supported or getting executed. So that's the reason we cannot apply this particular concept, that is a software based solution, that is what we call it as Peterson solution, to your critical section problem. But the way it has been explained, if you can utilize that, you can create multi-dimensional algorithms using which we can try to solve the problem of your critical section problem. Well, till here we have actually discussed in the previous section. And if you have still doubts, you have to just watch my previous video so that you can get a clear idea regarding that particular thing. And today's session, we are going to actually focus on these two things. Something we call it as synchronization hardware, and then we call it as mutex blocks. Okay, so basically till now, whatever the solution we have seen till the previous session, that is with respect to your software. Now in this particular synchronization hardware, we are going to actually see the hardware solution. Basically, as I told you that we may be having a hardware and a software-based solution. So software-based solutions we have seen in the previous session, but today we will look around something called as hardware solution in our critical section problem. And after that, we will be focusing on something called mutex block, and this is also a hardware-based solution, but this is much more efficient when compared to your synchronization hardware. Okay, because synchronization hardware, whatever the algorithms we are going to see for overcoming this critical section problem, they are somewhat complicated. Yeah, it's somewhat complicated for the program of implementation. So to overcome that, we will be using mutex blocks here. So here the operating system designers actually developed some tools, and that tools are actually nothing but we based upon this mutex block. So I'll tell you what I mean by mutex when we will be discussing that and how this block is going to work. Okay. So let's don't will not waste any time. Let's enter into the topic here. So the first thing what we are going to discuss here is synchronization of your hardware. So basically, whatever the solutions we have seen earlier now, those are purely based on software. That is nothing but your Peterson solution what we have seen. But apart from that, actually, we know that this cannot be implemented in modern days computer architecture, whatever we have. Well, in coming scenarios, we have several techniques. Not so it is the initial stage, but nowadays, if you can see, as the technology has been emerged and all, lot of new techniques have been generated. Lot of techniques have been created, developed, and these techniques actually provide solutions with respect to your hardware as well as with respect to your software. So in this particular session, we will be discussing about hardware-based solutions. Hardware-based solutions. And remember one thing, whatever the techniques that we are going to discuss here, all these techniques are based upon only one particular technique, based on one particular theme. You can say something called as locking, or other words, you can say something called as lock. Means whenever a process want to enter and execute in a critical section, it has to first acquire a lock. So when it enters, it acquires a lock and enters into the critical section. And at that time, no other process can enter into the critical section because it is already locked. So whenever a process completes execution, he will be releasing that particular lock and he will intimate the remaining processes who are waiting for that. So any one of the process will be entering into that particular critical section. And the same scenario is followed. Before entering, that particular process should acquire a lock. Okay. So the lock, I think you people will lock your rooms. Okay. So whenever you're coming in, so for example, whenever you're entering into your room, you will be simply locking your room so that no one else can disturb you. You can't be preparing for your main exams or something like that. So once you're opening that particular lock, then only others can enter into your room. So the same thing we are doing here. So we will be acquiring lock here. So okay, so whenever a process want to enter into critical section, it should acquire a lock. And once that particular process completes the task, he should release that particular lock so that other process can try to acquire that particular lock. This is the whole functionality that has been used in your hardware-based solution, what we are going to discuss in this particular thing. And one more thing, what I have already explained here, something called as acquire and release. Well, these are the two functions what we are going to use. These functions are atomic in nature. Atomic in nature. What I mean by atomic in nature is nothing but uninterruptible. These are uninterruptible, means whenever one of the process acquires a lock, no other process can and try to acquire that particular lock. That permission is not provided. That's what we call it as atomic in nature, not uninterruptible. It cannot be interrupted. Okay, so that is what actually basically happening in this particular thing. Now let's discuss about this particular hardware-based solutions here. Well, basically what I explained here, let's start with a single process system. So if we talk about a single processor system, what we have here, we can avoid this particular problem by making sure that whenever we are sharing a variable, let us suppose we have a variable, shared variable. Hence, let us suppose this particular variable is actually shared by two different processes. So whenever we are making any modifications to this particular variable, making sure that no interrupts are taking place, no interrupts are taking place when the modification is done to this particular variable can avoid this particular what we call this mutual exclusion problems and all. Okay, so what it means to say simply here is that if we can prevent interrupts from occurring whenever a shared variable is getting modified, we can make sure that whatever the update we might be doing to this particular shared variable, that will be done without any error. Because for example, if for example we have two processes P1 and P2 and we have a shared variable called as V. Now this particular process is having an access of that particular variable only for reading purpose. Whatever it might be some kind of file, and this process is executing a read function. At the same time, this particular process P2 is trying to access this particular file. Okay, let us suppose variable V, and he is trying to modify it. He is trying to modify that particular variable. Now, what will happen exactly here? Now, if another process comes, P3, he also tries to simultaneously access that particular variable B, and he is also trying to modify the operation. That is nothing but write operation he is performing. So P3 and P2 are performing write operation at the same time. Then what is the situation of this particular file? Definitely whatever the data this P3 and P2 are giving, that will not be synchronized properly. And whereas coming to this process P1, he has already opened simultaneously. So he might have opened the previous older version of that particular file. So he will not be able to get the modified version of that particular file. You got my point? So that's the problem that we do have. So to overcome that, what is saying that whenever we are making any changes to this particular variable, like suppose P2 is actually trying to modify a variable 2, then we will not allow P1 and P3 to access that. That is what we call it as interrupt. So whenever any process want to access a file, that will generate a interrupt. Even if I'm writing, you people might be thinking that I'm drawing like this. This is the interrupt that has been generated on this particular slide. So that interrupt we are actually stopping it when one of the processes is performing an operation on that particular file. So once this process completes it, then he will release it and then this process can perform. P3 can perform the operation. Once P3 has completed executing it, then P1 will be accessing that file and he will get the modified and the latest version file with respect to whatever the variable he is trying to access. I hope you people got a very good idea with respect to this. So basically what is saying that in a single process system, in a single processor system, make sure that no interrupts takes place. No interrupts takes place when executing or modifying. When we are modifying a shared variable. But the question here is that can we apply to this particular concept for a multi-process system? We are talking about a single process system. Means within a system we have only a single processor which is executing, and in that we are applying this. But can the same thing can be applied onto a multi-process system where we have multiple CPUs, multiple processors? Can we apply the same concept there? Well, definitely we cannot apply the same concept there. Yes, we cannot apply this particular concept when we have multi-process system. When we talk about your multi-processor system, we cannot apply the same concept. Why? Because let me explain you. There will be a time delay. There will be a time delay. See, whenever an interrupt takes place, that interrupt will be transmitted to all the processes. So whenever interrupt takes place, that interrupt is actually sent in a format of a message to all the processes which are working here, so that they can come to know. Like suppose one process is entering into critical section, an interrupt will be transmitted to every processor indicating that the P1 has entered into critical section. So then the remaining processors may not try to enter. So here, in case if you are disabling this particular interrupt, then what is the situation? Simply, you can understand now, these messages will not be transmitted to this particular processor. Then what will happen? No one will come to know that whether anyone is already executing in the critical section or whether anyone is trying to enter into the critical section. If not, I can try to enter into critical section. So this information, they will not have any kind of clarity. And when they are not having any clarity with respect to it, no one will try to assess. Means since no one is having any clarity, shall we enter into critical section or not? Definitely, what will happen? There will be a delay. Okay, so delay is nothing but it is proportional to your time consumption. So lot of time will be consumed or it will be wasted to enter into the critical section of the process, because let us suppose P1 want to enter into the critical section, but he doesn't have any information whether this particular critical section is free or whether it is busy, when someone might have accessed or not. Similarly, these processes are also having no idea whether this particular critical section is free or not, but they are ready to enter into critical section. But because of that particular dilemma, they may not be able to enter. And later on, by the time they enter, there will be a lot of wastage of your time. So this is what the reason why we cannot apply this particular to a multi-process system. The same thing what we had discussed about, something called as no interrupts. No interrupts. When we are updating a shared variable. Okay, so this cannot be applied for your multiprocessor system. So then the question comes is, okay, what solution we can design? What solution we can design to overcome this? Fine, we are saying that we cannot apply interrupts, we cannot stop interrupts. So interrupts will take place. So multiple process might be executing on that particular variable. So how to make sure that at a time only one process can perform operation? So definitely we need to design a solution for that particular thing. And for that, we are going to discuss about two hardware solutions here now in the coming slides. Two hardware solutions we are going to discuss in this coming scenario. And these hardware solutions are nothing but test and set. And same way we have swap and modify. Yeah, these are the two hardware solutions what we are going to see in your synchronization hardware. Okay, first let me show you the block diagram with respect to your this concept what I am explaining here. Okay, you can see, okay, sorry. You can see here, as I told you about acquire, like if you can see, this is your, I think you people have a clear idea now, this is your critical section, right? Critical section skeleton. If you see here, I think you might know what is this. This is your entry section. This is your exit section, what we have. And in between we have here a critical section and a reminder section. So we can see here, what did I told you that whatever the mechanism what we are going to see, that is your test and set, compare and swap. So these are the hardware solutions what we that have been designed, and these solutions actually work on a concept what I have already told you, that is nothing but lock mechanism, and this is a structure for that. So in the entry section, whenever the process want to enter in the critical section, he should first try to acquire the lock. Once the lock is acquired, no other process can enter into critical section except the one who is having this lock, and he will perform in the critical section. And once he completes the task, then when he comes out of the critical section, he will be simply releasing that particular lock and remaining process continue. And when he is releasing this particular lock, another process may try to acquire that particular lock and perform its operation, so that synchronization can be maintained. You can see that whoever is having a lock, only they can perform the operation. Means at a time only one person is actually executing, or one process is executing his task. No other process is doing it. So here that synchronization is maintained. That's what we are going to discuss in this particular thing. So let's see test and set instructions. Well, if you talk about this test and set here, you can see this is a normal, okay, this is a structure that has been used for your test and set instructions. As I told you, this particular structure uh, will be executed atomically. Atomically, I think you people might have understood now what do you mean by atomically, uninterrupted way. So it will be executed in a uninterrupted fashion here. And moreover, if two processes, I mean executing simultaneously, for example, this particular code, two processes P1 and P2 are executing in a two different CPUs, then this will be done sequentially, means one at a time. First P1 will be executing, then P2, depending upon the scenario. If P2 has acquired the lock first, then P2 will be executing first, and then P1 will be executing. So if you see here, it is using a Boolean variable called as target, and this is used to determine whether we can allow a process to enter into critical section or not. So this is the one. So and remember, this is a hardware-based solution. Hardware-based solution we have written in the software. So Boolean test and set. So we are going to get a variable called target, and that variable we are assigning to this Boolean array. And you can see this is a pointer pointer variable what we are using it. And later we will set that value as true. Okay, so whatever the value we are getting, we are storing it here, and then we are setting the target as true. Means we are saying that that particular process can enter into critical section. Okay, and once this is done, we are returning that particular value. So this is the way how it exactly this test and set condition does. It simply what it is going to do is it will simply execute. It will first test what it is going to test, whether the critical section is what we call free or not. If it is free, then set. What do you mean by set? Set that particular process which has actually called this particular instruction, test and set. So whenever a process wants to enter into the critical section, he should acquire a lock. That lock is this. So he is going to call this particular function, test and set. Now within this test, it will determine whether the critical section is free or not. If it is free, it will set this particular process to this particular critical section. Means a lock is acquired. So using this particular code, whatever is written. So then automatically this process will be executing in this. The remaining processes will be waiting for their term. And once he is completed, again, and then process P2 will be acquiring the log. Then process P2, what he will do, he will execute this particular test and set condition. Then he will get the log and he will try to access the information. And in this way, the whole process keeps on rotating. This is the way how exactly your test and set is going to execute. Okay, I hope it's clear with respect to this particular scenario. Same way, we have, okay, so this is the way, okay, he has given a code here with respect to your critical section skeleton. You can see here, this is what we call entry section for your critical section, entry section. This is your, I think you might be familiar by now. I don't have to write each and every time now. Entry section, exit section. So you can see here we are using a variable called as lock. Okay, so test and set lock, and this lock we are sending it as a parameter target. Okay, and if that particular lock is free, then that value will be set as true, and this will be transmitted back here. Now that particular process will get a lock. In case if the value is not true, I mean it is already acquired by some other, then this target will not be true. So this condition fails. So when this condition fails, automatically what the process has to do, he has to simply wait, do nothing. That particular process has to wait until this lock is free. When it is free, automatically it will be set to that true, and then it will be given to it. And once the process is given a task, he will be entering into critical section, perform his task, and when he's coming out, he will set the lock again to false. So when he's setting the false, the another process when it comes, he will be calling this particular test and set condition, this particular lock. Now this time this is false, means empty. Right now it is not been accessed by any other. So critical section is empty. So immediately what happens here, so lock will be becoming, so lock is equal to true. Means it is acquired by some other process, P2. Let us suppose P2. Now he is performing in this critical section. Once that is done, he will again set the task lock equal to false, and then he will come out. So this is the way how this particular process is going to execute. And you might have seen that from the beginning when we have discussed about critical section problem, you can see that this whole scenario, the concept or the syntax is same, but only thing internal logic is getting changed. So what is the syntax we have here? Entry section, critical section, exit section, and reminder. So this is common. There is nothing changed in that. Where the change is coming is the logic, whatever we are writing with respect to your entry section, exit section. Okay, and coming to remaining section, whatever it might be. So this is the way how it exactly executes. And the next hardware instruction, what we have here is something called as compare and swap. Now this, unlike your test and set, this particular, there we are using only a single variable, single Boolean variable, and that is nothing but we have used a target. But not like that. In this particular scenario, we will be using three different parameters, int value, expected, and the new value. And the initial value will be replaced with the new value whenever the lock is available. Whenever the lock is not available, the previous value what is there, that only we are going to store it up. So this is the structure of your compare and swap code. So previously what we did in your test and set, The same thing we are doing it here, but we are doing in a different manner. This is a different logic, that is a different logic. But ultimately the task is same, acquiring a lock. So whenever the process want to enter in critical section, he should try to acquire a lock, and that is what we are doing in this particular scenario. Okay, so what happens here? The lock will, okay, in this case also we are going to use something called as lock. So lock can be either 0 or 1. So 0 in the sense it is busy. Okay, sorry, free. 1 means it is busy. Means already someone has acquired that particular lock. Based on that, this particular scenario is going to see. So whenever the first process is going to call this particular function, let us suppose the process P1 has called this particular function, the original value of the lock is equal to 0. So what will happen? Automatically it will set to 1. Means initially it is free, no one has acquired. This is the first process which came. He has executed this particular step, that is function, compare and swap. So at that time what he will found is the lock value is equal to 0. What does that indicate? So that particular lock is free, means critical section is free. Then automatically the lock value will be changed to 1, means this lock is given to this particular process. Now this particular P1 will enter into your critical section. Another time at the same time P2 will come. P2 will call this particular function, compare and swap. So when he is calling that, he will find out that the value of lock is equal to true. What does that mean? Already some process is already acquired that particular lock. So at that time what he will do, process P2, he will not do anything. He will simply wait until this particular process is releasing that critical section. So this is the way how it exactly executes. So remaining steps are same like we discussed earlier atomically, so it will be executed atomically. You can see one after another. So P1 is having a lock, he is executing. Once it's coming out of the critical section, then P2 can enter into the critical section. So one after another, it is actually executing, and that's in an uninterrupted way. Means no one is interrupting P1 to come out of the critical section when he is executing it. So that is what the main reason of your atomically, the term called atomic. Okay. Now here we have the variables here. We'll be setting the variables whenever the value becomes expected. Whatever the expected value we want, like something P2, what he wants, the lock value false. So if it becomes false, if whenever they are checking the condition block is equal to false, then we'll set the new, this particular value with the new value. So what is the new value we have false? That we are going to acquire here. So the new value is true. That value we will be acquiring it. Okay, let me explain it so that you don't have any confusion here. Suppose P1 is there. So initial value he is expecting, suppose, let us suppose it is 0. Okay, he is expecting 1. So new value will be 1 in case it is 0. So if the expected value is 1, so what does that mean? Someone has already acquired the lock. So the initial value will be same. So the value will be 0. But in case if the expected value what he is doing is wrong, means initially 0, then this particular process can be given the lock. Then what he can do, automatically this new value is 1. This value will be replaced with this. So here it becomes 1. So the lock is acquired by this particular process P1. So this is the way whole this particular works. Well, we will not be executing this program. These are done internally. That's the reason I told you these are hardware-based solutions. We are simply writing a code which will be implemented internally within the system. Okay, hardware-based implementation. That's what actually going on in this particular thing. So let me show you the diagram here with respect to your compare and swap so that you can get a clear picture now. So you can see here, this is the way how it takes. You might have seen that almost it is same, right? You can see here, this is your entry section, this is your exit section. And you can see earlier we used here test and set. Here we are using compare and swap. So here we are using three parameters. Address of lock. What is the lock initially? 0. Then what the value this particular process is expecting, initial first process expecting is 0. So what is the new value we require? Since the value of a lock is 0, that means it is free. Now we need to allocate that lock to that particular process. Then the value of the process will becomes 1. So the new value 1, expected value is 1. So these three we are transmitting here. Here the process will check whether it is free or not. The lock is free or not. If it is free, their values will be swapped. This one will be here. It will come up here. Then that particular process will require the lock, perform the operation. In case that is not the scenario, do nothing. So just wait for the other process to release the lock so that it can get and it can perform the operation. And finally, remember, once you are completing the process enters into the critical section, perform the operation. Once it's coming out, he has to set the value of lock to 0. Then only the next process can try to access that particular critical section. Okay, so I hope it's very clear. So these are the two hardware-based solutions that what we do have. But basically, these two solutions, what we have discussed, we know that there are three conditions that need to satisfy in order to provide a solution to your critical section problem. What are those? So first one is mutual exclusion. Then we have something called as bound waiting. And finally, we have something called as progress. Well, if you talk about the previous uh, method, what we have discussed, that is test and set, test and set. And this method, compare and swap. These two actually are only mutual exclusion. Yes, these two are actually satisfying only mutual exclusion condition. But what about bound waiting and progress? Well, these are not able to execute. I mean, not able to satisfy these two requirements. So this is not a 100% genuine solution for your critical section problem. So how we can provide that means we'll be combining these two terminologies. I mean these two, and we are going to get this particular thing. Yeah. So we are going to combine that compare and swap and this, and then we'll come out with this particular solution. You can see here. So here we are using two different data structures here in this particular scenario. Okay, this is a bound waiting condition with respect to test and set. So we are using two different variables here, Boolean waiting n, Boolean lock. So I think you people might have no idea about lock. This is a variable used. Okay, so value can be either 0 or 1. 0 means it is free. Lock. Okay, the lock is free. 1 means it is acquired by some process. So Boolean waiting n means the number of processes who are waiting to acquire this particular lock. So based on that we are waiting here. So this is your entry section now. You can see there is a much more code. So we are using a terminology called as key. You might have known about this. Key is nothing but this is something like turn. We use the turn in your Peterson problem. So same way here we are using the terminology called as key. So waiting of I is equal to true and key is equal to true means that process is ready to enter, acquire a lock and enter into the critical section, and it is that particular process turn. So both the conditions are true, then what they are going to do, it will execute this particular test and set condition. And here the acquired means the lock will be given to this particular key, that particular process. And then waiting of I equal to false, why we are doing this? So once that particular process completes some thought, he has to wait. Okay, so later on it has to wait. The remaining processes has to wait. Now enter into the critical section, perform the operation. Once you are performing the operation, you need to come out of the critical section. Yeah. Okay, so when you have people coming out of that particular critical section, what we need to do, we need to set the lock as false. And same way that particular process should also be conditioned as false. Okay, so lock, why we are doing false, since it's coming out of that particular critical section, so definitely the condition has to be set as false here. And same way, whichever the other process is waiting, means this particular process already entered into the critical section. Now, just now he has came out. We can't allow this process to enter again immediately. So for that condition, we are going to do it as waiting of j is equal to false. Okay, well, if you're possible, you can take some example and you can try to execute this particular code. You can get a clear understanding of how this particular thing works. Okay, and this is purely based on your hardware-based solution. And this actually supports your mutual exclusion, your bound waiting, and coming to your progress. All these are actually satisfied in this particular scenario. And then we have something, a new topic here, something called as mutual lock. Okay, so till now whatever we discussed is totally your hardware based solutions. Now here in this case, the operating system designers, what they did is they were not satisfied with this hardware based solution. Why? These are very much complicated. You might have seen how complicated they are. When you are trying to understand that, these are somewhat complicated. So for that purpose, this software designer, they started developing software tools. And in that tool, they started using this particular mutual lock concept. Well, don't get confused with respect to what is this. This is the same whatever we had discussed in the previous one. So mutex is nothing but MUT is nothing but your mutual. EX is nothing but your exclusion. And I think you know what you mean by exclusion here. This is your one of the requirement of your critical section problem. Okay, mutual exclusion, bound waiting, and progress. The mutual exclusion short form he is using. So here he is directly using law, which is of type mutual exclusion, and based on that he is going to perform the operations. Let me show you so that you can get an idea. Yeah. See here, this is the diagram what we do have here. You can see here, do acquire lock. You might have understood now. So this is a function here, and for that function, we have a code here. Same way we have release lock, exit section. Here it is. So if we talk about here acquire lock, what we are doing, we are using a variable here. This is a variable, and this is a Boolean variable. What we are actually using it. It indicates whether a lock is available or not. Now this is the one which determines either in 0 state or 1 state. So 1 means busy, 0 means free. If it is free, then automatically it will acquire, means that particular process will acquire a lock. If the lock is 1, means it is busy, then the system has to wait. That particular process has to wait. Same way, whenever the process whichever enters into the critical section and perform the operation, when it's coming out, he will be calling release lock. So here release lock will be available equal to true, means that particular lock is now available for access by some other process. That is what he's saying in this particular thing. So this is the way it exactly works. Okay. Here, uh, the thing, what we need to concentrate here is, it's very easy. I think you people might have understood now how it exactly works. Acquire log busy. But only thing what we need to concentrate here is that this particular method, this mutex lock is having some disadvantage. This mutex lock is basically having a disadvantage. What is that is, it requires busy waiting. This solution, whatever we have provided right now, this will require a busy waiting. Okay, busy waiting in the sense nothing but other processes which were busy waiting in the sense nothing but, see, when one process is actually in the critical section executing it, another process will come. This process will first call acquire function, right? It want to enter. Now, when it identifies that someone already having this means process P1 is using, process P1 is already in the critical section, he will be waiting for some time. Again, what he will do this particular process after some time, he will again call that acquire. And when it is calling it, it will determine that this critical section is again present with respect to that particular process P1. After some time again he will, so what happens here, this particular P2 is entering into a looping statement. He will after some time, he will keep on calling acquire until he is getting it. That's what we call it as busy waiting. Sometimes we can also call this as a spin lock. Spin lock means it will keep on spinning for that particular lock until he is getting that particular lock. So this is one of the small disadvantage what we have, because here whenever the spin lock takes place, the CPU cycles are getting wasted. Instead, these CPU cycles may be used as some other process for performing execution. So that is what he's saying in this. So these CPU cycles, whenever this pin lock takes place, some portion of the CPU is getting wasted. That's what the main disadvantage that we have with respect to your mutex clock. But that doesn't mean that it doesn't have any kind of advantages. It has advantages also. What is that is, there will be no context switching takes place. Context switch is not required. So we don't have to care about context switching from one process to another process, so whether it is doing perfectly or not, that we don't have to see. Why? Because you can see here, when one process is executing in the critical section here in this case, P2 is keep on spinning, means context switching is taking place here, isn't it? So P2 cannot enter into critical section. When P1 comes up, then P2 can enter. So context switching takes place perfectly one after another. So you don't have to write any code, or you don't have to worry about context switching related issues. So that is one of the advantage of your mutex. So even though it has a disadvantage, that spin lock, busy waiting takes place, still it has an advantage also. So we can utilize them in our system in our coming scenarios with respect to different techniques upon our requirements. Okay. Okay, we'll wind up this particular session here itself. In the next session, we'll discuss about the most important topic what we have, that we call it as semaphores. Yes, this is one of the most important topic of your part 1. Semaphores, and then we have monitors. These two we need to work on very well. These two we have to focus on. Okay, so these two are going to play a very vital role in your this particular part 1. So please make sure that you people are watching this particular videos perfectly. And if you have any doubts, you people can just ping me up. Okay, so I will respond to your queries, whatever you people might have having. Okay, thank you. Thank you for watching this video.